So we going to apply the Ampere's law to get the expression for the magnetic field inside a solenoid. So you now know what a solenoid is. What we are looking at here, this picture is a cross section of a solenoid. Half of it is behind the screen, half of it is above the screen. So here it says the current is coming out. So I will write this is what is coming out of the board wire, and going in, then it is going. Right, let me make it dash line. Okay. There it comes out. Yeah. No, we have to finish. Still few slides left in chapter. I will not, I mean, once I finish it, I will do questions, okay? I will not start a new chapter, okay? All right. So this is, of course. Okay. All right. So we are going to use Ampere's law to get this expression for the magnetic field inside the solenoid. So this is a cross section of a solenoid, that's this picture. So you can see, you know, the current is coming out, and that will be what you see out, jutting out of the screen, and then it goes in this wire. So I'm using dotted line. Sorry. Yeah. Then and so on. So what is coming out will come out from the left side of the coil of the solenoid and go in on the right side. So now you understand how to get the magnetic field direction. You curl your fingers in the direction of the current flow. So the thumb tells you the magnetic field will be up inside this solenoid. Right, now let's apply the Ampere's law. What is Ampere's law? This is the equation of the Ampere's law. Sum of this product parallel component into delta L, we apply through a cyclic path, okay, closed path, and sum them up, and we say it is equal to this constant mu0 multiplied by the current inside that cyclic path we choose. So the dotted line here is the cyclic path. I'm going to use, let me use red. So I'll start from here, and I will go in this direction, and this counterclockwise, no, clockwise, and come back to the same. As you go around that line, it's a closed path. You will compute what is on the left-hand side, and we'll say it's equal to mu0 multiplied by the current enclosed by this red cyclic path. So that's what Ampere's law. Let's see whether we can use Ampere's law to get the expression for the magnetic field inside a long solenoid. Right, I will break this into 4 segments. The wire number 1, which is inside, and wire number 2, the second horizontal, then wire number 3, and the wire number 4. So I'm going to break into these 3 parts and evaluate all of these one by one. So on the wire number 1, the magnetic field and delta L are in the same direction. And from symmetry, we have a parallel component parallel to the delta L. From symmetry, I can say it is a constant. I can take it out of the summation. So what we have is the total length. All the delta L collected will be this length. We're calling it L. So I will write L. The sum of the delta L will be L, and the magnetic field is the same everywhere. So that is easy to calculate that this integral with the summation. Number 2 is this wire. right? The wire on the top, number 2. There we have to consider this part which is inside the solenoid and the other part which is outside the solenoid. For the part that is inside the solenoid, there is a magnetic field, but the magnetic field is vertical and the delta L is horizontal. What is the angle between them? Well, it's 90 degrees, right? So the magnetic field has no component it has no parallel component parallel to the L. That means this is 0. There is magnetic field inside, but it has no component parallel to delta L. Therefore, this part will have 0 contribution. What about this one? What is outside part of the wire 2, which is outside of the solenoid? There are no magnetic field. In a perfect ideal solenoid, a long straight solenoid, there is only magnetic field inside, no magnetic field outside. Therefore, this is 0 anyway, no contribution to this summation. So therefore, this will be 0. Number 3, this part is also outside the solenoid, no magnetic field. Therefore, this is also 0. Then finally, we have this. It is similar to the number 2. This part has no magnetic field, therefore it is 0. The part that is inside, although there is magnetic field, it has no parallel component to the delta L, therefore that is also 0. Then the right side of this Ampere's law has mu0 and the current enclosed by this cyclic path. So we have not just one current, one loop, we have n number of loops. So we have to collect, say, for example, here we are showing 1, 2, 3, 4, 5, 6, 7, or whatever number of loops. So we have to multiply the I from each loop by the number of loops to get the total current. And then we finally, here L goes to the other side. Then it becomes N over L. We get the expression which we presented to you before. So we have proved the equation for the magnetic field inside the solenoid using Ampere's law. All right, so let's go to the next slide. The last section, the last topic in this chapter, magnetic domains, or the effect of electrons to make something magnet. We know if a current flows or if the charge is moving, it will have magnetic field associated with that. But you also have a magnet, right? Bar magnet, permanent magnet. This permanent magnet has magnetic field around it. How did it get the magnetic field? Is there any charge moving inside? Well, it consists of atoms. And any individual atom will have electrons moving around the nucleus. So we can say that is a current. We can say, for example, that reason for the magnetism is these electrons are charges, or the charges are moving, therefore we should have a magnet from any atom. But it doesn't happen like that. You don't have everything magnetized, right? So why? If you just calculate this electron motion about the nucleus, just take one electron, it go around the atom very fast. In this much of second, 10 to the minus 16 second, it will make one round. So this will correspond to, if you just do classical calculation, it will correspond to 1.6 milliamperes of current. Okay, but this will, because the distance is so small, this will result in a magnetic field of 20 Tesla at the center of the circular path. Okay, if you use our equation, the classical equation. But we don't see everything is magnet, right? If you take an atom, it is not a magnet. What happens is, you don't have just one electron. So there are many electrons, and they go around in any arbitrary direction. So magnetic field coming from one electron will cancel from magnetic field coming from another electron. So in general, the net result is the magnetic field will be 0 or very small for most material. But we have another thing called the spin. So electrons go around, that is the orbital motion. The electron can spin. It's actually not real physical spin, the classical spin, but it's a quantum effect, okay? But anyway, we can kind of model it as a spin like this. So if this is the electron that you see this picture, it may be spinning about an axis at the center. So, then using our right hand thing, and if the charges are moving like that, then it will have a magnetic moment this way. But actually, because the negative charge, electrons are negatively charged, so the magnetic moment will be the other direction. For a positive charge, it will be just curl it and that way. But for an electron, which is a negative charge, it will be the other direction. So we can say that because of the spin, we can have a magnetic moment. Anyway, it's not an actual spin, it's a quantum effect, keep that in mind. But we can just model it like a spin. This field, due to the spinning, is generally stronger than the magnetic moment from orbital motion. Okay, it's much stronger than the magnetic field from orbital motion. But what happens, these electron spin, they pair up. If one electron spin is upward, another electron with the spin down, they will pair and it will cancel the magnetic field. One is up, other one is down. So it will cancel each other. So probably in chemistry, probably learned about spin, right? Spin up, spin down, they will occupy the energy level. So usually what happens if you take an atom, as much as possible, they will pair up, okay? They will in the same state, one will be up, the other one will be down, so the magnetic field will cancel. But for some atom, you will have the odd number of electron which is not paired up. Okay, so that is where we will have the magnetic moment. Iron is such an atom. I think it has 3 unpaired electrons, so it will have a magnetic moment. Electrons usually pair up with their spin opposite each other, so their field cancel each other. That is why most materials are not naturally magnetic, but we do have some material. In some material, the spins do not naturally cancel. Such materials are called ferromagnetic. You know what is ferro mean, ferrous? What is ferrous? Iron. Fe. You know this, don't you know your chemistry? Ferro. Iron, right? Yeah. This is iron, yeah. We don't say iron, we say in the periodic table. So that's why, because ferrous, so iron has unpaired electron, so they will have they can be magnetized, and actually these permanent magnets are made of iron. Now, excuse me, please. In a ferromagnetic material, let me go to the next one, you can have domains. Atoms that are having their magnetic moment aligned in the same direction, they will group together and they will create regions or domains. So in this domain, all the atoms have their spin aligned, say, in this direction. And the adjacent domain, another one, they will have in another direction. So it will be all random. There will be domain, not just single atom. There will be lots of atoms in that domain with the same spin alignment. But we will have so many other domains. The net, if you take the whole thing, they will cancel each other because the orientation of this domain is random. One domain will be, say, to the left, the other one will be to the right. Something will be to the top or maybe in another angle. So it is all random. So if you take the net magnetic moment, it will be 0. So that is how it is, okay? So we can take a piece of iron, which is ferromagnetic material, and it is not normally ionized, magnetized. But suppose we bring or keep it in an external magnetic field. We bring another permanent magnet, which is magnetic material. So you bring it close, and let's say magnetic field direction is that external direction. Then what happens when you apply an external magnetic field? The domains that are more or less in the same direction as the external magnetic field, like this guy, they will grow in size. Maybe they will recruit atoms from the neighboring domains, and it will grow in size, because this is almost in the same direction as the external magnetic field. So for example, if you look at this, it is smaller compared to that one, because in the opposite direction. And this guy, another one, grown bigger. Those who are already more or less in that direction of the external magnetic field, they will grow in size. Those that are not opposite direction, they will shrink in size. So what happens now, if you now calculate the net magnetic moment, there will be a non-zero magnetic field, a magnetic moment in the same direction as the external magnetic field. So it effect become more pronounced. Suppose I increase the external magnetic field, you see that this domain even grows much bigger than before. So it can become stronger, magnetized strongly than this guy when the applied external magnetic field is smaller. Okay, so that is the domain theory of explaining the ferromagnetism. At the beginning of this chapter, we talked about hard magnetic material and soft magnetic material. So if you have a hard magnetic material, the domains, after we get it aligned, even when the field is removed, external field is removed, they will stay magnetized, okay, for hard magnetic material. But for a soft magnetic material, once you remove the external field, thermal agitation, the heat energy coming from the environment, is enough to return it back to the random state, so it will become unmagnetized. There are applications of this ferromagnetic material. So suppose you have a solenoid or electromagnet, and you can keep inside that electron, in the core, we can put a piece of iron, a ferromagnetic material. Then what happens? The domain inside this ferromagnetic material, iron core, it is usually iron core, we call it core, which is kept inside this electromagnet, they become magnetized. Thereby, it will increase the magnetic field from the electromagnet. Okay, it will enhance or increase the magnetic field. So there's one use of this ferromagnetic material. We keep it inside the core of the solenoid. It will increase the magnetic field. Types of magnetic material. So we already saw that this ferromagnet, they have permanent magnetic moments. So once you magnetize it, we can, it will be there permanently. That's why we have these bar magnets, permanent magnets. They will align their magnetic moment as a whole domain in the direction of the applied magnetic field. Paramagnetic, it's similar to ferromagnetic, but the response is weaker. They have magnetic moment that aligns with an external applied magnetic field, but the response is weak compared to the ferromagnetic material. So the types of material. And another one is even very strange. Okay, we can only explain this using quantum mechanics or quantum physics. When you apply external magnetic field, what happens? They will align in the opposite direction. The magnetic moment of the atoms of this magnetic material, they will align in the opposite direction. So it cannot be explained using classical model, but so we don't have to worry about how it happens. It's a quantum effect. So, but it is in the opposite direction, but again it's very weak, okay, compared to the ferromagnetic, even paramagnetic, it's a weak response. Then recently they even discovered another type called the altermagnetic. I will not go into the detail. It differs from all the other three. It has some strange properties. If you want, you can look it up. Right, that ends this chapter.